I do feel pretty bad about what I did. So it's going to follow essentially these two. Sorry? What? I'm not saying anything technical yet, so it's fine. So this is what we're going to cover. First, we'll do approximation theoretic results in deep learning. This is probably all we'll cover today. Oh,
sorry for the interruption. I was wondering if it's better to zoom in because people might be able to see better.
Yeah, sure, we can try that. Yeah, my bad. And then the third lecture will be optimization and some small amount of generalization results also in deep learning. I should say that these will be deep learning focused, but first, they won't be purely what's in the notes of mine if you've seen those. And second, they will, I'll have some mentions of LLMs, though I won't do too much explicit proof. And then 4, I'll do approximation theoretical results for LLMs. And one reason is that it'll be completely distinct is that I've mentioned that for deep networks, people mostly took a real valued type perspective, but for LLMs, people have really taken a computational perspective, treating an LLM as learning algorithms. So, okay, so this is the plan for these lectures. All right. So I'll just go ahead and start with 2. And I'm going to show you 3 things for 2. Just get the order right. Okay. Okay. I'll just say I'll reorder it in my head. I'll just do 2 things. So the first one is a classical theory, just as warm up. This is something called universal approximation. And it's sort of a classical thing that everyone used to sort of associate with deep networks for reasons I honestly don't really understand, because it has nothing really to do with deep networks. It's very strange that some sub-community that people kind of revolved around this. And then I will talk about refined size estimates. So this first theory will it's basically a sanity check, and it really breaks down when you try to port it over to LLMs. And the second one, it doesn't give any reasonable estimates on the size of a neural network to solve a problem. The second one is what the community ended up really doubling down on the last decade to try to explain the empirical success of deep networks. And we really only made small progress. And I mention that just because for everything I mention here, it's going to be clear that we answered only infinite number of zeros, 1% of the interesting questions. But basically, the community has moved on to LLMs. So bit of a sad situation. Okay, so let me just go ahead and start blasting through some of this classical approximation theory. So actually, I can just stick it right here. So the goal in 2A is a sanity check. It's that for all continuous functions f from Rd to R, and for all epsilon greater than 0, there's going to be an element of, let me just change these letters. There's going to be an element of some function class that we care about. So this is going to be some deep network. Will be an element of some function class f such that in some norm we care about, this thing, I'll just make it a triple norm to make sure it's not doesn't look like a 2 norm. This thing is less than epsilon, okay? So let me tell you why I'm teaching this. So the reason I'm explaining this is because I'm going to give you So I'll just tell you that I'm going to show a versatile generalization you can basically apply to anything. In other words, I'm going to show you a generalization that I hope you basically look at any network and you don't have to concern yourselves whether it's true or not. You shouldn't be like stressed that because the width isn't large enough, it's a problem or something. Okay, so this is the good thing. This is why I'm still showing this, and sort of it's a basic theory that everyone is expected to know. On the downside, I'll just say that it's true for all ML methods. This is why I'm extremely confused why anybody ever thought this was a theorem that has anything to do with neural networks, is there is not a machine learning method in use that does not satisfy this condition. If you use an SVM, you're going to use it with a powerful kernel that satisfies these conditions. If you use boosting, it's going to use blah, blah, everything I could possibly say has this property. So it's very strange for me that this was ever associated with neural networks. Let me also just make a historical comment. So the first relevant proof is arguably due to Kolmogorov in the 50s. So Kolmogorov wrote a limit theorem, and if you truncate the limit in his proof, so if you take his proof, there's a limit in it. You truncate the limit, you get this theorem. So you actually reduce his theorem, you get this. Sorry? Calligraphic F. Oh, deep network. Sorry, DN. Yeah. Yeah.
I understand the last one. All methods, like if okay, it's like linear regression.
It's not true for linear regression. So all ML methods used in practice.
Okay.
Yeah. Yeah. So basically anything people use has some sort of like feature knob at a minimum, linear regression on top of like hand-coded features. So yeah. In other words, this thing never explained why. Yeah, like another thing about it is that the classical proofs of it, they went through polynomials.
Yeah.
So if you're writing a proof through polynomials, why not use polynomial predictors? But we don't use polynomial predictors anymore. So, okay. Okay, so let me give you a quick intuition. So this theorem will be, it'll cheat a lot. So it'll look like this. So my F here will, so all of these theorems are going to look like the span of something. The span can be interpreted as the last layer of the network. And when I say span here, I mean in a functional sense. So you should take this as the set of all possible linear combinations of all finite sizes. So it's not a finite dimensional span. It's an countable, all countable linear combinations. Okay, so these things look like X maps to, and then I'm going to have one activation, and then I'm going to allow myself to have, in this theorem, I'll be just very, because I was so informal earlier, I'm just going to be a little bit more precise. I'm going to allow myself this many nodes on the inside. Get my indexing, okay. All right, AI, okay. And then I get to add in another, I can add in another scalar over here. Okay, so it's this class of functions where AI is in R to the D, BI is in R to the D, and R is in, sorry, these are in R. This one's in R. Okay. Okay, so this is my function class. So it's 3-layer networks. I have an input, a ReLU, another linear, so a linear combination, ReLU, linear combination, ReLU, and then another linear combination. Okay. You can think of this as 3-layer networks. And for this proof sketch, I'm going to use a ReLU. So this is Z maps to max of 0 and Z. Also, I'm really abusing the fact that you guys said you're zooming in on the board. So I apologize. You shouldn't have told me that because now I've like reduced my font size. Okay, so given this function class, I'll have that for all epsilon greater than 0, for all continuous functions G. from RD to R. I'm going to have the fact that if I look at f x minus gx, it's going to be less than epsilon. Now, I should say that every time somebody writes one of these theorems, you have to ask what the norm is. And for this one, we're going to cheat. We're going to use a garbage norm. And then I'll show you how to do a better one, but this one has like a clean picture proof that actually illustrates some issues with using deep networks. You have a question? Because it doesn't really say much. So in particular, you could have a prediction problem where all the action is concentrated in a small volume of space. And this, you can get epsilon error just by ignoring that region of space. So when people prove these theorems, they also have a fairly garbage norm they use, which is just the supremum norm. So you take the supremum over all x. So when we get to that one, you can ask me for the technical reason why that is also a garbage norm. Is there another question?
With the expression you've written, how is it possible to ever get something negative out of that? Because you have the signal revealing outside.
Yeah, span.
Oh, right, okay.
It's a good question.
Are you taking the closure of the span too, or just the span?
We don't need closures in this theorem. Okay, so let me tell you the proof sketch. And I should say that for the proofs today, I will, with the exception of one where I reduce to a lemma, they're all going to be sketches. Go on. What's the question?
This may be a dumb question, but what exactly does the sigma mean?
Oh, yeah, here it's the ReLU. It's this, I can make this larger. So in this one, it's going to be the ReLU, which is z maps to max of 0 and z. Okay. So I'm going to reduce the problem to an easier one in a way that might seem pretty natural. It's going to be that I'm just going to claim that there exists a piecewise constant function h from r to the d. And just to be clear, when I say piecewise constant, I mean that it's going to look like I equals 1 through, I'll just pick some scalars, and then I have indicator that x is in region R. And without loss of generality, I can take these Ri's to be open rectangles. So Ri can be equal to, or open cubes. So this can be the product of AI, the open interval AI BI. I don't think let me actually pick different constants because I used AI. So I'll use CI and DI, okay? So this is a partition of the space, and it's a summation over those. Okay, so the claim is that there exists such a function with h of x minus g of x is less than or equal to epsilon over 2 for all x in the cube. Okay, I'm not going to dwell on this. This fact is in like chapter 2 of every undergraduate analysis class, which I don't mean to be condescending. I mean, either you took the class or you didn't. If you forgot the class, it's a consequence of compactness, like the total covering definition of compactness. So the way to think about this is that I have some continuous function, and then what I do is I grid the input space, and then at every grid cell, I just form a very small piecewise approximant, and I'm saying that within this grid cell, the function values of h and f are close up to epsilon over 2. It's kind of intuitive that for a continuous function, you can shrink this gridding such that you eventually get closeness up to any epsilon over 2 you want. Okay, so I'm taking that as a lemma just because it's in a textbook and most of us will never care. Okay, So there's this, and so now I've reduced the problem to approximating this. Okay? I say I reduced the problem to that because I have the span out here. So I'm going to pick so we'll pick F. Our F is going to be equal to the same outside, but then in here, I'm going to pick Fi of X, and this thing is going to be approximately equal to the indicator of X is in Ri. Okay? So if I want this entire thing to be like epsilon over 2, then if I make every one of these close to this indicator up to epsilon divided by 2 times the L1 norm of all the alphas, then the overall thing will be epsilon over 2 close, and I'm done. Okay, does everybody follow this claim? Did I say that too fast? Yeah, you have a question? No, it's continuous over a bounded set, so it's... Oh yeah, all of these theorems, I should have mentioned this. Every one of these theorems always has a bounded domain. If it doesn't have bounded domain, consider the sine function. The sine function has infinitely many oscillations, so you cannot approximate with a finite combination of functions with finitely many oscillations. So all of these theorems must have a bounded domain. But a good question. Yeah. Okay, so we'll pick this. And so note that f of x minus h of x by triangle inequality will be less than or equal to sum alpha I times fi of x minus indicator x is in Ri. Okay, so if all of these, if I make this less than epsilon over 2 times the sum of all the alpha i's, then these will cancel and this thing will be less than epsilon over 2. I can triangle inequality, I get epsilon for the whole thing. Okay, so I've reduced the problem to this right here. Okay, and the reason I'm rushing to this point is this is where something interesting happens. The rest of this, if you've taken too many analysis courses, is easy. But that's not really like machine learning is my point. Okay, so we're going to focus on this, or rather this part. Okay, let me show you why this is cool. And here I'm going to go slower.
That is going to be in our class.
Yeah, but inside the span, the thing inside the span. Yeah. So I'm actually going to write that out. So our goal is find Fi, which is going to be of the form, so I'll just write it out explicitly. It's going to be of this form. Oh, sorry, I'll make it really explicit. It's going to be this. Then I have to pick, I actually forgot what letters I wrote, so I'll just make some up. This was 4D. And then I think I had an R over here. Okay, so I have to find these numbers, these numbers, these numbers, which is close to this indicator. Okay. And I've told you that the solution is going to use 2 ReLUs, but does anyone want to feel like doing it with only 1 ReLU, 1 layer? So remark. So why not, for instance, why don't we just do this? Why don't I just choose something, this M can be as big as you want it to be. And I'll pick slightly different. I'll just use the same ones. Why not? Okay. Does everybody see what I'm saying? So this does not have any easy solution. This is why I'm doing this theorem. Is there a question in the back? Yeah. So I just want to be clear. So this theorem, before we do the more heavyweight ones, I'm using an extra layer, right? I have multiple layers. When I do this theorem, when I do the official one, I'm not going to have this many layers. Here I'm allowing us extra layers, which are not necessary. So this statement is definitely true. You can definitely do this, but I think it's really valuable to try to do it in your head. I mean, let me explain. I mean, if I have a square, right, that's what this is, and I'm trying to approximate this, I mean, what are you supposed to do, right? Like if you just put ReLUs kind of on the bounding hyperplanes, okay, then what you get is you get 0 in the corners, you get 1s here, and you get a 2 in the middle. See, I put ReLUs like this, ReLUs like this, like this, like this. So these are the function values I get when I add it up. So if I wanted, if you want to do this with only one layer, you seem to have to do really crazy stuff with really subtle cancellations to actually get 1 in here and 0 outside. Like, I'm not sure everybody's following my point, but let me make a more clear version of this remark. So because m is on the order of 2 to the d. So it's not exactly in the literature, but you can essentially prove that if you tried to do this, you need the number of parameters to be exponential in the dimension. And I'm not using exponential dimension, I'm using linear in the dimension. Okay, does everybody follow this point? So this is just a remark inside of a proof, but the point is that sometimes 3 layers better than 2. So if you use 3 layers for this, you need this exponential size. But if you use 2 layers, then you need a small finite size. Right, I think I said that backwards. For 2 layers, you need exponential size. For 3 layers, you need small size. Okay, but just to be clear, let me just work this out in more detail. So if I build this representation up in stages, if this is the rectangle that I'm trying to approximate, first I put ReLUs like this. So I get 0 up here, 1 over here. I get this function, okay? It's 1 in this row, it's 0 in this row, it's 0 in this row. I put a ReLU with a high slope, I get up to 1, and then I negate it and I go back. Okay, so 4 ReLUs. And then if I add 4 ReLUs in the other dimension, I get to this one with the 1, 2, and the 1, like this. Okay, and then if I subtract off, so this is a 2-dimensional example, but if I subtract off 1.5 from each of these, or let me just subtract, sorry, I don't know why I was making it. Oh, actually 1.5 is correct, sorry. I just subtract off 1.5 from each of these. Okay, I really should have used 2 layers in the output. So, I mean 2 ReLUs in the output, but too late, my mistake. If I just subtract off 1.5 in each of these. Okay, and then you apply a ReLU to this, you're gonna get zeros everywhere. Or let me actually use a different color for this. I'll get zeros everywhere. Except in this entry, I get 0.5. Okay, so I've achieved my goal of finding a function which approximates the indicator. Yeah, so I'm zeros here and I'm 0.5 here via the use of a second layer. So what I should have done is I should have allowed myself the use of a constant there, and then this would have been a 1. I messed up. I should have put that 2 in there, yeah?
Why you're using 4G and not exponentially ReLUs? But then K there is arbitrary, right?
Yeah, K is exponential in D. Yeah.
So why is it that essentially you're saying that this is 3-layer? In one layer, the width is linear, in the other layer?
Yeah. So the only claim I'm making is that 3 layers is going to give me a small representation for this indicator. But for the general original problem, it'll still be exponential. Yeah. Actually, I'll make a formal remark about that in just a second. So thanks for prompting. Okay, let me go through the whole proof from beginning to end so that everybody, because I know that there are a lot of tangents. So let me just first say the proof from the beginning again, and then I'll explain the tangents in a bit more detail. So this is our first baby intuitive theorem saying that some reasonable neural network can approximate any continuous function. We're cheating in 2 places. One is I'm allowing myself 3 layers. So I'm counting it as 1, 2, and then 3 for the span. And the other place I'm cheating is I'm using the integral norm, which, as we mentioned, can just give up on regions that are actually very important. Okay. And then the way the proof worked was I reduced to a real analysis lemma. And then, by the way, I'm not trying to be condescending when I say like this is an analysis lemma. I'm one of these people that took like 1,000 analysis courses, and like, I mean, I'm just saying like, it was not maybe the best use of some people's time. Okay, so I've reduced it to an analysis lemma. The analysis lemma tells me that if I want to approximate this continuous function, I can instead approximate a piecewise constant function, and then the f I choose can just be given by the parameters of that piecewise constant function. So if the piecewise constant function was some alpha I 1, and then the indicator on the rectangles, I've reduced it to the problem of approximating these rectangles. And maybe I did the triangle inequality too fast for you, but you can check that if this accuracy is epsilon over 2 times the sum of the alpha i's, these cancel, and I just get an epsilon over 2, so I've finished the problem. Okay, so I've reduced it to this. And then I said that I can solve that first by having 1 layer, which sort of does larger prediction on the middle than everywhere else, but it's not quite clean. It can't get zeros outside the region. It's just larger in the middle. And then I can subtract off this offset r. So this is the r this is this one right here. I make it negative 1.5 or negative d minus a half. And then I do another ReLU and I get to the value I want. And just to be clear, the reason I do the integral here, not the absolute one, is I didn't say what goes on in these in-between regions. In these in-between regions, I get the wrong answer, but I can shrink that to be arbitrarily small in volume, and that's how the integral works out. Okay, so that was the proof. I hope it makes kind of fun geometric sense. You just stack these ReLUs together and get the answer you want. An important tangent I had was that if we were going for an intuitive proof, it seems almost impossible to solve this inner part geometrically. Okay, it's very hard. And there's a theorem in the literature that essentially tells you that if you try to do this, you'll need exponentially many ReLUs and like careful cancellations. And as a final remark, so this goes back to Siva's point. So remark, so a size estimate of 1 over epsilon to the d is inherent when the target function is all continuous functions. So one reason that I personally really dislike having all continuous functions as a target is just take the following, even make them Lipschitz functions. Okay, just pick any random string of length 1 over epsilon to the d. Does everybody see where I'm going with this? Pick a random string. Okay, we know that random strings are in general incompressible. So just take it and just hide those bits inside the cube subdivision of the, okay? There's gonna be no simple representation for all of these functions. So if you're compressing random strings of size 1 epsilon to the d, you need 1 epsilon to d parameters. There's no way around this. So with a bit of work, you can turn this into a formal lower bound that says that if you're trying to compare against the class of all continuous functions with an epsilon accuracy, you need this many parameters, or else you have to fail on some constant fraction of the functions. So yes, this 1 epsilon to d is inherent with this goal. And it's one of the reasons why classical theorems could not capture the real reason we use deep networks, which is that they don't have this exponential penalty. Okay. Okay. All right. I hope that was somewhat intuitive. Okay, any questions about this? So I told you that I was going to show you some lemmas that were kind of versatile. So I'll do that for you now. There's actually, so to prove the stronger version of the theorem, version with the correct norm and only 2 layers, it's just a one-liner. Of course, it's just a one-liner that invokes the textbook lemma. So, you know, but here it is. And I'm going to call this a lemma because I'm going to use the special activation, and then I'm going to get corollaries for any activation you want and other generalizations. Okay. So the lemma is going to go like this. So I'm going to set my calligraphic f to be the span of just the exponential function. Okay. The exponential function has the cool property that if we added constants on the inside, it's equivalent to scaling by a constant on the outside. So you don't have to use biases. Okay. Okay, so this is our function class. And now we're going to prove that for all epsilon greater than 0, for all continuous g, there exists an f in calligraphic f such that this holds, and I'll just take a supremum here. Okay. So this is sort of the right version of the theorem. And so this has a very short proof. I'll show you corollaries you can apply to almost anything. But again, the reason I'm showing you this is that if you ever come across the need to prove such a theorem or you see it somewhere else, I recommend doing it the way I do it here because it just really makes it very short. So the proof is via something called the Stone-Weierstrass theorem. And I should say that once you invoke this theorem, so the Stone-Weierstrass theorem, it's a theorem that says that this conclusion holds, this second line holds, for any calligraphic f which is roughly polynomial-like. Okay, so that's the lemma. And so for this lemma, you just have to check essentially 5 properties. And the first 3 are very natural. They're very easy to check, so I won't say much about them. So there are 5 properties to check. So the first one is that every element of the class is continuous. So that is easy. The other one is that for every x, we have a function which is not equal to 0 exactly. We have that by construction because exponential is not 0 anywhere. So not equal to 0 for all x. This is also easy. And the third property that's easy is that it's closed under vector space operations. So in other words, taking linear combinations. F is a span, so that one's also easy. So again, what I'm advocating here is that here's a very powerful theorem if you ever want to prove a result of this type. We just have to check some desiderata. These were the first 3, they're easy. Now we're going to check the more interesting ones. Actually, I'll do it over here. So the first one is that we separate points. So in other words, for all x prime, there exists f such that f of x is not equal to f of x prime. such a condition is clearly necessary because if there were 2 points where all the functions in the class agreed, then we couldn't model functions where they can disagree. Okay, so this is a very natural property. For us, it's very easy to check. We can just consider the following function. Z maps to exp of, we're just going to take a single node network which points in the direction of the difference of these two. Okay, so I can look at z minus x interproducted with x prime minus x divided by x minus x prime squared. So this is in the class without even invoking the span. It's just one element. If you expand the square and divide, then I can get this thing. Okay, you can rewrite it in the same way. Oh, I guess I am using the span because I'm using the coefficient on the outside. But yeah, so this is in the class. Okay. And this function has the property that it's equal to 1 if z is equal to x. It's equal to e if z is equal to x prime. So it satisfies this condition. Okay. Is there a question?
Which form of the stone wire stress theorem are you going to use? Because because the stone wire stress, this is as I know it, is for the supremum norm on continuous functions, whereas you were talking about like this one norm thing with the integral.
Yeah.
Or did I miss that?
The supremum norm is here.
Oh, I missed that in other words. Thank you.
Is there another question? Yeah, if you're actually curious, the version I'm using here, it's in one of the standard analysis texts these days. It's by a guy named Folland. There's like an infinite number of versions of this theorem and an infinite number of proofs. I also really like the versions in the Barry Simon books. Okay, the other property we have to check is that we're closed under products. And that also goes through pretty easily for us. So if I multiply two of these together, oops. Okay, so here's two elements of the class, and you can just combine the sums. Let me just write it as a double sum. Oh, sorry, wrong index. So when you do the product, you can combine these inside the exponential and okay. Okay, so again, this is the stronger form of the theorem. The idea to use stone Weierstrass was in a paper by a couple authors. I remember Hornick and Stinchcombe were on it. I remember those two authors. This is from like 1989 or so. The paper is about 30 pages long. They did not use the exponential function. So if you use like a modern treatment of the stone Weierstrass, the exponential, this is the complete proof. I didn't miss any details. But as you can see, it's completely opaque. It invokes a textbook theorem. And we'd have to prove this. There are many ways to prove this. If it was just polynomials and not polynomial-like functions, then you can use interpolating polynomials and just manually check the error. That's one way to prove it. And one thing I want to say here is that this one also has the exponential size because when you have to do these products, you end up with an exponential size. So all the ways to prove the Stone-Weierstrass theorem, they sort of end up with an argument that if you study the details, seems to be exponential in dimension. So I'll put that, I won't write it as a remark, it's kind of consistent with the other remark, but the constructions of this proof always seem to have an exponential dependence on dimension. Okay, so now let me give a few, oh crap, I can't move this board. Okay, that was a miscalculation. Okay, now I should remember not to use that board. Okay, are there any questions while I erase? No questions.
Yeah. I mean, this slightly relates to what I asked earlier. So here you're going to use Stone-Weierstrass to basically density in the supremum norm.
Yeah.
And then is the plan to then somehow use that to go back to the original like L1 type norm you started with?
Well, over the bounded interval, the uniform dominates the L1. So
So that's immediate.
no, but the L1 is weaker. I don't want the guarantee in the L1. I want it in the supremum norm.
Oh, and I think I misheard her. I'll ask you.
Okay. Okay. Okay, so I have a few, I'll write these as remarks. Okay, and let me just recap the theorem that I hid from you, which is, recall, we have a theorem that says for all epsilon, for all, and this is the definition of universal approximation. Okay, for all epsilon, for all continuous G, there exists an F, which is in a set of two layer networks. So there are two affine layers and one exponential layer. Oops. Okay. Such that okay. Okay, so that's the theorem I just wrote. And let me just make one remark that this is for the exponential function. So just a quick, so we can make the theorem and I'll explain what I mean by any other activation in just a second. So I can replace this exponential with any sigma via univariate approximation. Let me explain what I mean by this. So the proof gives us a representation of this form. So we have some exponential, this thing. So all we need to do is take any other activation and approximate the exponential using a linear combination of those. And then we plug that in, move the sum outside, and we solve the problem with any other activation. So for instance, if we were using the ReLU, we would make a piecewise affine approximation of the exponential just by putting ReLUs at all these points. Okay? I'm treating that as easier because univariate approximation avoids all of this exponential dimension stuff I was talking about. You can just sort of move forward since it's a monotone function. Okay, so The other reason I'm leaving it in quotes is there is a formal theorem of this type. The formal theorem is pretty cool if you've never seen it before. So this is from 1992. They say that so suppose sigma is continuous, and they're able to prove the following. They say that f, so I'll call this fx for using the exponential. They say that f sigma, so if I just replace exponential with any sigma, they say this is a universal approximator. If and only if, so that's the interesting thing, it's two directions. Sigma is not a polynomial. Okay. So that's their theorem. No one looks happy except for me, but this theorem is cool because it's an if and only if. So actually the direction which is new is easy. So if sigma is a polynomial, so if this is a polynomial, it's a polynomial of fixed degree. So this has fixed degree, and the linear combination of polynomials of degree r is still a polynomial of degree r. So in other words, I can't even approximate certain polynomials of degree r plus 1. I can just have r zeros in the function. Sorry, r plus 1. Okay, so that direction is actually easy. So if we are a polynomial, we can't be a universal approximator. The other direction's pretty crazy. The way it works is it says, okay, so yeah, so this direction works by contrapositive, and it says that if sigma polynomial, then that implies that f is poly of same degree. Okay, so that's busted. The other direction, we consider two cases. So the first case is sigma is C infinity. What that means is that C is infinitely differentiable with continuous derivatives. If you can do this, then that implies that this class is closed under differentiation. So for any function in here, its derivative is also in there. And you use that to get a really slick approximation proof. That's all I'll say about it. And then otherwise, you convolve sigma with a Gaussian, and you get a C infinity function. Okay, so this proof probably just looks like jargon to most of you. I just wrote it up there to interest you if you might be interested in checking the paper. But this is sort of the strongest version of this type of theorem you can possibly get. It's an if and only if. Is there a question?
Like the f sub sigma mean.
Right. It means that this symbol here becomes sigma. Oh, I should actually, sorry, I realized there's something missing. My bad. I forgot the bias needs to be added. I was trying to be too quick about it. So this is span X maps to that activation, but now I need to add the bias. Sorry, I don't need the J's. Okay. Yeah. So it's the same as the exponential, but I've replaced the exponential with another activation, and then I have to add the bias because I was using a trick to get rid of the bias for the exponential. You look unhappy. Is this good or? It's a two-layer network.
Next, about the next theory. Shouldn't it be easy to if sigma is a polynomial, then shouldn't you have like a polynomial of like it's
I think I anticipate where you're going. Are you saying if we had arbitrary degree polynomials, would be fine? Because that's true. Was that not where you were going?
like you had a linear polynomial, but then you kind of you have a linear approximation.
I think we're disagreeing about what's approximating and what's being approximated. So we're trying to approximate a continuous function. So in particular, I could try to approximate a function of high degree. Okay. Did that resolve the issue?
Yeah.
Okay, cool. Okay. Okay, so let me continue with the remarks of okay, another one is that, so all of these theorems, they require a very large width network. So this span, as I've mentioned, will necessarily have an exponential width, exponential in the dimension. But we can also turn it into a theorem where the depth is exponential, but the width is constant. So let me explain how that works. So the theorem also works for residual networks of any depth. And what I mean by this is you compose together functions of this type, where f of x is equal to x plus gx, and g let me make this a z, sorry. Okay. Okay, g is at least as expressive as just a single node network. So whatever function class you draw g from, it has to contain all functions of this type. And z is in dimension r to the order d. So let me explain how this is proved. So what I can simply do is I can take this construction and I can just make it vertical. So if I have my input x, I can just make the x accessible everywhere in the network. And I have another accumulator variable which starts at 0. And I add in the first node of the network. And then I add in the second node of the network, and so on. Okay. So again, what I did was I took this representation, which is a sum, which is typically thought about as a large width network, because I get the input and I feed it into m nodes, where m is exponential in dimension. I can instead write it out vertically and have a bunch of residual connections just moving that upwards. So this says that a constant width high depth network can also approximate any continuous function. This is closer to what's used in practice. We don't use arbitrary width networks, we allow both the width and the depth to increase. So in particular, let me just say many papers, a few years back, there was sort of like a cottage industry of reproving this. So many papers proved that the ReLU network of width d plus 2 and arbitrary depth is a universal approximator. Okay, and again, all it does is it takes that construction over there and puts it on its side. Instead of having a bunch of nodes next to each other, they are on top of each other. And I say a ReLU network, so we don't have residual connections, but you just move things you shift things to be positive and use the fact that the ReLU is an identity mapping over the positive orthant. Okay, any questions about this? So I'll make one last remark about this. Which is what happens if we apply this to a transformer. Okay, so remark. So for a fixed n, the transformer is a universal approximator from on the sequence space of dimension d times n. So we have the d-dimensional tokens or the token embeddings, and then we have n of them, and we map between those. Okay. I'm not going to say in detail how to prove this. There are many versions of this result in the literature. You can also use what Kolmogorov discovered in the 50s, which is because we're not constraining anything in the network, we're using real numbers. What we can do is we can pack the entire n element context into one real number. Okay, so here's the solution. Trivial solution. Use a space filling curve. So use a very complicated network. To embed r to the d to the n in a single real. Then use the MLP universal approximation theorem. So the MLP in a transformer is a universal approximator. We use one MLP to do this embedding, use the attention of the MLP to do this embedding, and then we do another one to solve the problem on this embedded representation. Okay, this is a theorem you can prove. A lot of people have written this paper up. Okay, these papers exist. But I'll just give the citation to Kolmogorov 60s. Okay. Does anyone see anything wrong with this? Yeah, go on. Rigorously, it's true. I mean, you can prove this. So morally is more what I was asking. Yeah.
Morally, has anybody found any empirical evidence that the networks actually use?
Sure, you can give more moral complaints too.
Also, morally, the size of the network in the part of the space node is probably going to get enormous.
Yep. You want to keep going? Yeah, so I think it's actually, I can't tell if you could read my vibe, but I think it's very important to have this perspective because when transformers started coming out, there were a lot of papers doing real valued approximation and doing real valued approximation on sequence spades. And the community transitioned into doing bounded precision computational perspectives. And I think these comments we just heard were basically the reason. So I'll summarize a version of them. And thanks for the answer, because that is basically exactly what I wanted. So I'll say it this way. So So this construction destroys the purpose of multiple attention layers. So sort of the intuitive way to pay attention to a transformer is that it's an alternation of layers, one which mixes information between tokens, one which works token by token. So if we just use some hammer to move everything into one token, we didn't even need an attention. We should have just had neural network with d times n parameters in the first place. There was no point in ever having invented attention. Okay, and that's related to the other comment that he just made, which is that if I said that the MLP is going to be exponential in dimension, the dimension here is d times n, not d. So the MLP will have size okay. So is there a question? N is the length of the sequence. So just to remind the whole audience, the transformer takes in a sequence of length n. The sequence is broken up into inputs, each of which have dimension d. So what this construction is doing is it's taking the entire sequence, which has n elements, each of dimension d, and it's just packing them in a single real number. So I have to say that when I started working in or studying transformers, I was obsessed with real valued perspectives, and I myself kept converging on solutions like this, and I thought they were really clever. And my colleagues actually pushed me in the direction of doing a computational perspective. So I'll say that a simple fix which changes the perspective entirely you bound the precision of all operations. Okay, so you require all of the weights and all of the intermediate computations to have at most some number of bits. If you have some number of bits which is finite, then which is bounded, then you cannot pack d times n inside of it. So it just refutes this. Now it also kind of moves you out of the space of doing real valued computations. So it has that loss, but it is a way to remove these sorts of space filling solutions. And even though a lot of you might be surprised I'm even mentioning this, I mean, this is used in a lot of papers. So, and this solution always exists. You can just say one attention layer or just forget the attention layer and just have a fixed embedding. I should say this also highlights another thing about the attention, which is really important, which is that you, of course, could just do sequence-to-sequence mapping with an MLP, but then the MLP needs at least n edges in its input if it's going to read the entire input, whereas the transformer has a number of parameters which is independent of n. Okay. So does anyone have any questions about these last remarks? Because I'm trying to, I mean, I'm drawing a line in the sand. I'm not talking about this sort of stuff anymore after this point, because I think this sort of killed it off. Okay, so in the last 25 minutes, what I'll do is I'll give some estimates for, so all of these are exponential in dimension, which means they don't capture the value of neural networks or deep networks. And now I'll give some cases where we have some estimates of the size whether they're good or they're bad. Are there any questions? I'm a little bit concerned that there aren't as many as in the first non-technical lecture. Now I guess you guys can also see why I was just so adamant about not knowing really what to teach, because this whole sort of progression, which comprises an infinite number of papers and an infinite amount of books and stuff, because of this issue, it's just not really used for transformers. Okay, so we'll do this for the rest of the lecture. Yeah, because everyone seems a little bit tired, I'll actually reorder what I was planning to do so that I do it in a little bit of a fun way. And then, like I said, the next two lectures we'll do a combination of optimization. And then for the last lecture, I'm going to do this stuff for LLMs. So just to give you a preview, so the LLM approximation literature, it's sort of converged on, I would say, two perspectives, which is using so one perspective is that transformer is equivalent to some class of circuits. And there are formal theorems of this type. In other words, based on some choices you make, you can make a direct correspondence between a class of transformers with certain restrictions on the weights to an explicit known studied class of circuits. And I should say that involved in this is that a transformer plus chain of thought, which is what I mentioned was this unbounded computation thing, you can also show that this is Turing complete. And just as a remark, RNNs, which I didn't define, but for those of you that know them, RNNs were also shown to be Turing complete, but they actually used these bit manipulation tricks. So the proof that RNNs were Turing complete from the 90s, it packed the entire state of a Turing machine into a single real number, which of course is not realistic. Okay, so there's this, and then the other perspective is based on communication. So the interesting bottleneck that seems to be arising inside of transformers is they have to communicate information across different ends of the transformer, between different ends of the sequence. And this seems to correlate with empirical observations of what's difficult to learn. There's even a paper that studied these communication problems and then fed them to things like GPT-4o and Gemini Flash and things like that. And they found that sort of the performance of those things matched their predictions based on this communication complexity. So this is a bit constrained perspective on function class complexity, which is completely different from all this real valued stuff. And this is what I'll show you in the fourth lecture. And as a person that's worked on both sides, it's just this divide over here is extremely interesting. Okay, so I'll tell you a little bit about size estimates. And what I'll do to make it a little bit more fresh, since I realized that a lot of the lecture was a bit dry and maybe a lot of you were thinking, why is he teaching this after he just said this stuff isn't important? So I'll give you a thought experiment, and I know there's at least one person in the audience. I know there are multiple people in the audience that know the answer to what I'm about to show. So if you've seen this before, maybe don't raise your hand. So like this is one of these like wrong answers preferred type questions. So I'm going to give you some data and I'm going to ask what happens. Okay, so I'll define the data over here. So I'm going to sample my x's uniformly from the corners of the hypercube. Okay, it's the L2 normalized hypercube. My labels are always going to be the products of the first two coordinates. And I'm just multiplying by d so that they're plus minus 1. So let me just make that explicit. Okay, and my predictor is going to be a 2-layer ReLU network without biases. Let me actually write out the ReLU just so everything is really clean on the board. Okay. And just to be really explicit, my loss is going to be the logistic loss. So the loss of a predictor over a finite sample is this, okay? Log 1 plus e to the minus yi fxi. This is binary cross entropy. Log loss on this like sigmoidal model of prediction probability. And then I'm going to use gradient descent. And again, I'll talk about this example more tomorrow, but for now, I'm just going to talk about it in an approximation theoretic way. Okay, so I'm going to talk about it, but I'm going to use this as motivation to talk about approximation theoretic questions. Okay, so I'm going to run gradient descent on this, which means my parameters at some time are going to be the old parameters minus some positive step size times the gradient of the prediction with respect to the previous parameters. And here I'm overloading notation. I'm making F be this prediction mapping with some weights W. Maybe I'll just write it this way, where W is all of these parameters, the A's and the VJs and all of these things. Okay. So these days, it always changes the way that people initialize these networks. It's many of the papers, they model it as a Gaussian initialization. Last I checked, it's actually uniform per coordinate within a variance which matches the variance of a Gaussian. The statistics, I mean, a lot of the math works out equivalently for this initialization and Gaussian initialization, even though this was not rotationally invariant. But just morally, let's treat it as a Gaussian initialization. So what I'm drawing here are the first 2 dimensions. And if I project this problem onto the first 2 dimensions with Gaussian initialization, all of my weights are sort of going to be on the surface of the sphere. So what I'm drawing here are A1 times V1. I'm drawing the products of the weights, okay? A1, V1, A2, V2, and so on. And they sort of concentrate on the surface of the sphere. Okay? Okay, so let me just explain what's going on here. This is the data. All the action in the data is in the first 2 dimensions. So I'm just going to talk about what happens in the first 2 dimensions. At initialization, AJ times VJ, I'm just trying to show you some way to visualize both layers of the network simultaneously in the same 2 dimensions as the data. They're sort of on the surface of the sphere. And I'm going to run gradient descent on this example. And initially, the ReLUs are sort of pointing in uniform directions. So does anybody know what happens if you run gradient descent on this instance? I know a few of you know, because a few of you have, at least one of you have seen me giving it a talk, and I know actually that, yeah, basically I know that all the speakers know what happens. So thanks for not raising your hands. But so it's actually pretty miraculous, and let me say why. I mean, if you hadn't run it, and this theorem has not been proved in full generality, there's no reason not to believe that all of these lines sort of extend. I mean, there's no reason not to believe this. But actually what happens if you run gradient descent is most of the points approximately stay put. And the ones that are kind of winning, you just extend in these 4 directions. So it just extends in these 4 directions. And as time goes on, as these directions get longer and longer, eventually you only have one node pointing in the 4 directions. So what I'm saying is that as t goes to infinity, the weights converge to, there are 4 weights which converge to, where these things converge to plus or minus 1 in the first 2 coordinates and 0 everywhere else. And all the other weights basically look like 0. Oh, to be clear, I'm normalizing all the weights when I have this discussion. So I'm talking about this. So 4 of the weights go this way, 4 weights do this, and everything else goes to 0. Okay, so again, let me explain this one more time. So I have m weights, make m like a billion if you want. You can make it much larger than dimension. I'm saying you run gradient descent, no regularization, no nothing. Just run gradient descent on this unregularized, unconstrained objective. Run it to infinity. Okay? And what you get is a solution where eventually just one particle is moving in each of these 4 directions, and it converges and normalized to this direction. These 4 directions. Okay? Proving this in this generality is still open. The closest proof we have is one by Margalit Glasgow, who's right now a postdoc at MIT. She has the closest we have to proving this. She basically proves this just under 2 small restrictions. So she uses SGD, she makes these norms equal at initialization, and she makes the initialization small. And she has this proof. If you haven't seen this before, this should look utterly remarkable. That gradient descent on a dense thing is turning into this specific sparse solution. Oh, and I should say that these things are hard to prove. So the paper that proves this is 50 pages long. Just for this data sample, if you increase this product to be 3, no one on Earth knows how to prove it. If you make these 2 not equal at initialization, no one on Earth knows how to prove it. So yeah, it's very difficult. Okay, does everybody get this? So the reason I'm telling you about this to motivate these size estimates is there's actually a formal way of talking about what this converges to. But while I'm erasing, does anyone want to ask about this example? This is like my favorite, this example is like my favorite thing in all of deep learning, pretty much. Yeah?
So it converts to those 4 non-zero values. Does that actually exactly get this XOR?
Yeah, it gets 0 test error, 0 training error. Yeah. I'm about to show you it's like the optimal solution in like a certain regularized sense. Yeah. I should have clarified that this problem is you can get 0 training and test error with a sparse solution.
You talked about multiplying 3 things, x1, x2, x3. In that case, is it even possible to get 0?
Yeah, it is. So for that one, you need a larger solution, but no one's been able to prove it. People have even spent like 100,000 hours with Margalit's proof trying to make it work for 3. The solution for 2 has like, so it turns out that the product of 2 or 1 has special structure which is not shared by 3 or more. Like if you put me on a desert island for 10 years and said you can only get off if you can prove this, I'd probably just say like, just throw me in the water. Unless, I can call Margalit or something. But. Yeah. Yeah, oh, and by the way, another reason that I'm, so like, somebody called me cynical in the break. It's because an LLM embeds a deep network, but we can't even answer questions like this. So. Okay. So let me tell you why I used this to sort of wake everybody up and talk about approximation theory. So Francis Bach, he made 2 very interesting function spaces related to neural networks. And they're called the F1 and the F2 spaces. I think the title of the paper is Convexified Neural Networks. Is this paper, right? Yeah, okay. So let me just show you what FP looks like. Okay, so I'm going to write down F subscript P for a different P norm, and then a bound, and it's going to look like this. By the way, I'm going to write not exactly what he talks about. I'm going to consider a simplification just to make some technicalities easier. But I'm going to look at the class of functions of the following type. So I'm going to take X and I'm going to map it into, okay, so what is, this was of course discussed before. I can view a very large width network as an infinite width network, and I just write the infinite width network as an integral. Now, if I wanted to deal with the technicalities, I'd make this a general integral over some general measure space. I'm just going to write it as the density. So that's the one cheat I'm doing, which is simpler than his paper. But suppose I have some basis class where I can write f subscript x of w, and you can think of this as being, you can think of w as being a pair, like w is equal to v comma b, and this is a single node network. Okay, so I have some class of basis functions. It can be like all possible nodes of depth 1, and then I have a density on the w's. And then this, for instance, let's say the density on the sphere. Okay, and so what I might consider is oh no, I have too many p's in here. Let me make this q, sorry about that. Then I have a norm on this, and I'm saying this is at most b, okay? And let me call this over here, let me call this star. Okay. Okay, so if we do the optimum over f1 of b, now let me just note for the experts a little bit of a technical issue for the L1 norm. This thing actually blows up. The limit points are these spikes, and so we need to take the closure. Just let me leave that out for now. So the optimum for star, if I call the XOR, this problem over here, if I call this star, is the 4-value solution. Okay. I can give an even stronger remark. So, and this is probably the most exciting thing about this for me, which is that to get test error epsilon on star with F2, and then the same question with F1. Okay, so what I'm asking here is forget gradient descent and all these things. I'm just studying it as a statistical problem. I'm trying to minimize, I'm seeing what test error I can get by having a fixed finite sample and minimizing this over either F2 or F1. Okay, so in one of the cases I'm looking for these sparse L1 solutions, in the case I'm looking for sort of dense solutions. Okay, for this one, we need d squared over epsilon samples. And for this one, we need less than d over epsilon samples. And this one corresponds to the NTK, or feature learning, or sorry, no feature learning. And this one corresponds to feature learning. Okay. So that was a bit of a mouthful. Let me explain it and then take questions, and then we'll be done for the day, I think, right? That's the correct timing, right? Okay. So I told you I was going to talk about size estimates, but then I sort of felt that everybody seemed either a little tired or did not enjoy what I did with universal approximation. So I jumped to something which is, yeah, at least for me, pretty inspiring. Hopefully it worked. So at first I told you about this 2 XOR problem, which might have seemed like a very big jump, but Then I pointed out that if you run gradient descent, it finds a very peculiar solution. And then I pointed out that there is a formal way to write down what that solution is. So gradient descent, when you do two-layer training, actually kind of searches over this F1 space implicitly. Yeah?
Q, or what is the L1 norm of Q being less than B?
Yeah. So what that ends up meaning here is that, so for this, I'm going to have to take the limit points of this, where this jumps to can do these point masses. But what you can show is that the minimizer over like the proper version of F1 is a probability distribution which just has mass on 4 points, and those 4 points are just pointing in those 4 directions, and each one gets mass 1/4. Yeah. Use the density, yeah. Yeah. I think
Just integrating.
yeah, that's right. Yeah. So I think yeah, and so if we were okay, just again for the experts, the reason I wrote it in this way, the proper way to write this is to have this be a measure, and then I don't have to make his limit points. Then we take the Lebesgue integral with respect to that measure, but then I have to use the total variation norm. I have to define the total variation norm. I thought it was just easier to use this like, this function space, this function space norm. So it's always one, but yeah, it gives a different class of functions and a different bias. So yeah, it prefers these yeah, it prefers these sparse solutions. Okay, let me summarize this as a remark and then see if there's any. So I'll make it like an open question. So open. We do not know in general, A, which solutions Atom and GD prefer, and B, their statistical properties. So this was one case where gradient descent chooses the F1 solution. You can actually embed the solution to NP-hard problems inside of F1. So people believe that F1 is not in general what gradient descent does, but people do not know what gradient descent does. I'll also say that some of the statements I made are false for Atom. So not everything I said was true for Atom. Atom does find orally the same solution, but it might move many particles in each of the 4 directions, not only one. So yeah. So in other words, we do not know in general how to characterize what function space really characterizes. And I'll probably make a quick remark about it, which was stuff I planned to talk about today, but just sort of skipped, which is things like the Barron norm and all these other norms that people use to talk about neural networks in a way which is not exponential in dimension by default. But overall, we really just do not know the structural characteristics of the networks that are learned in practice and how that influences everything else about the training pipeline. Okay, any questions about that before we stop for the day? Yeah? Yeah, I would even say that the relationship between the two is not fully known. Like I said, Margolit's proof, probably somebody, well, no, actually, I don't know how to get the moral equivalent to her theorem with just gradient descent. So yeah, the question is, there's also different versions for stochastic and non-stochastic. Some differences are known, so.
hopefully that